Thank you, Kai. Thank you for the invitation. Always pleasure to be in Heidelberg. So today, the lecture I'm giving is more of a lecture than a talk. The goal is to get you, after this, learning a couple of things. So it's not so much of an overview of everything that happens, but particular ideas. Okay, can you hear me now? It's for the video. Okay. So transfer learning. So I'm going to be talking about transfer learning. At least not working. So this is the outline of the talk. Why do we care about training sets? Because I'm going to apply transfer learning to training sets. How to generate training sets, an overview of transfer learnings, an overview of generative models, a little bit more than what Matthew talked about, neural network generative models, and then some methods we have applied. Okay, then the results. So let's start with why do we care about training sets? You have heard already about Astroinformatics and machine learning. And in order to do any machine learning, you need some examples for the machine to learn upon. That's supervised learning. So training sets are the pinnacle of everything. So as I said, supervised learning is building models by presenting some examples. And when we start doing this kind of business and machine learning for astronomy, everything was looking so good for a while. We're getting 95% accuracy left and right. We're beating each other. Everybody was very happy. But in reality, I think someone mentioned it earlier, is that we're only dealing with about 50,000 stars that are well characterized. So those examples we have, the training sets, are very hand-picked. Actually, it's totally ad hoc picked. So in order to go beyond that and build models, build systems that we can use for discovery, we need to really address the issue of training sets. Okay, so this is a very quick thing, but important. So let me go through the process of machine learning. So we start with some data, which we label, means we give them labels if it's a star, a galaxy, what kind of a star. And we have a bunch of things, most of it around here, which is unlabeled. So we split them. That's an important thing, training and testing. We learn on the training. We create a model, and we use the testing to evaluate. And once we're happy, we use the model to apply to the unlabeled data. That's pretty much machine learning in a nutshell. So important thing, remember this testing thing. But so now let me describe very briefly what I mean by label in case you know, some people have questions. Here is a classic thing, cats and dogs. For each animal here, I gave a label, cat or a dog. Very simple, right? Now, the importance of a training set, just to convince you that it's very important, is, first of all, size matters. In this case, it does matter. The bigger the training set, the better your model will be. It's less overfitting. So what you see here is some kind of a score, and this is the training set example. So what we're looking is the cross-validation meaning when you try the model in something you haven't seen, you see the score is getting better and better. On the training set, the ones you learn, it gets worse and worse. That should be obvious why, because you have more data to fit, right? If you have only one training set, of course you can get a model that works very well. Okay, so that size matters. And the other toy example I have, just to, again, put things in perspective, is the quality that matters. So for example, I have this nice training set here. I'm actually going to point here, so let's just all look there. So I have a lion, a tiger, and an elephant. I train a model nicely on this, and then I show the model this animal here, and I ask the model to predict. What do you think it's going to say? Good. I agree. That's what. Yes, the trunk or the neck. Okay. So having the right training set is important, because if you don't show the model everything there is, it's not going to be able to predict it. So we need training set that has everything. And also, if you look at here, these lions and tigers and everything, they're really nicely posing. And in reality, the images you're going to get, they're not going to be so nice and clear. So having a variety of your training examples is very important. Okay. So that's my argument number 2. My argument number 3 is that, okay, we hear about all these advance in machine learning, especially deep neural networks. And if you look at it carefully, all these algorithms were discovered about, I don't know, 30 years ago. So machine translation, for example, in 1988, it was there. It's only in around 2005 and beyond that machine translation start working. Actually, in the last 5 years, I would say, I can easily get an email in German and I put it in Google Translate and I understand what it says. And that only happened when we create a training set to train the models. The same even with convolution neural networks, ImageNet, which is the big success of Google in recognizing images. The convolution neural networks algorithms, the papers appear late 80s, early 90s. And again, and only until 2012, 2014, that the big revolution happened. And why? ImageNet. ImageNet is, at the time when it was built, about 1 million images, hand-labeled by people. So having a training set allows you to create the good models. Okay? So I hope by now you're convinced that we do need good training sets. And in particular, I think in astronomy, we do need better training sets. What we have is, I don't know, 200, 2,000 outliers that X person did, and some AGNs from Sloan, and something from Catalina. It's just all over the place. Okay. So what's the problem? The problem is that labeling objects can be extremely hard. You have to have people labeling objects, and people tend to do mistakes. Okay. So, all right, so now let's review how we generate training sets. So this is the way I see it. I think that covers pretty much everything. One is manual and visual inspection. You just get your images and you say this is an RLA or time series. You say Cepheid, this is a quasar, whatever. So you get one person to do that, or you get a bunch of people to do that just to speed things up and for redundancy. Okay? But that's, as I said, expensive. Means it takes a long time to create training sets of 500 million objects, right? Again, another way is called active learning, which is combination of manual inspection and using the machine. So what you do, you manually label things, and then you ask the machine to label things, to classify things, and then you say, where is the machine confused? And you take those and you give for the relabeling, okay, or for labeling. So that's better, but still involves humans. The other one is called synthetic data augmentation, meaning you create models to create stars, and since you create them, you know what they are, so you have the labels automatically. What's the problem with that? It's expensive, and you have the biases. The biases meaning we build the stars the way we want. We build the objects the way we want. And finally is transfer learning. Transfer learning, what it does is that if I have a data set in which I have created, painstakingly created the training set, can I use it for something else? Okay? So that's what I'm talking today. Okay, so let's go quickly what transfer learning, a little more in details. It's domain adaptation, transfer learning, kind of the similar ideas, is that you learn in one domain and you apply it to another. You learn in one data set, you apply it to others. You learn a language in English and you apply what you learn in English to Spanish. Surprisingly, it works very well, actually. Most languages have the same structure. You can learn German, and then whatever you learn in German, the grammar, the ideas, you can use it for English. So that's transfer learning and domain adaptation. All right, so I'm going to go a little bit simpler again. So in particular case, I'm talking if we have source data. So let's say Sloan has created the training set we want, and now we're going to use DDF, right? So we have some labeled data out of all the data I have, and I have a target data set, it's LSST. We don't have training sets. So the goal is to just take them there and put them there. Okay? Very simple. If you can do it like the PowerPoint, we're done. So sometimes, and that's an important, is that we can create a little bit of training set in the target data set. So this is what we're facing to do, right? So the task is how we move from one to the other. Okay? So let me show you some examples of how we do it. Again, this talk is going to be ramping up. The beginning is too easy, and at the end you lost me. So you see. So what we have here, the source data set on the left, you can see the gray points. Yes, you can see the gray points. I have a bunch of data, and I have a bunch of data that I have labels. The colors are the labels. The blue objects and the red objects. And I train a model, which is this line here, to separate. Once I have the model, I can even classify the gray points, right? In the target, I don't have any labels. You can see these gray points here. So the question is, can I take the model from the left and put it to the right, right? So if I do that, I go there. But is that okay? Most likely not, because things shift, right? Another way of seeing it, instead of transferring the model, I'm going to take the training set from the target of the source, and I pass it to the target. And once I have labeled data in the target, I'm going to train another model here, and I'm done. Okay? Any questions so far? Yeah.
In the second example,
yeah.
you have to train again. So what did you transfer?
You transfer the labels, and then you train again. But I have labels. I have training set. I can train now. Okay. So I solve the problem. Yes? Yes, that's the task. Bear with me. Okay. So let's see what can go wrong. Why can I take the model from one and put it to the other? Or why can I take the label data from one and bring it to the other? Let's see what can go wrong, right? So let's say I have in the source 2 classes. And in the target, again, but I don't have labels. So as you see, there is some shifting. Okay? So shifting can happen. Different filters, different background, different sky, different telescope. Okay? Another thing that can happen is we have observation biases. So I take Sloan, which goes depth 21, something like that, and then I go to LSST, which is going to go depth 24. It's going to be different populations. So as you see, now I have more of the left-hand side, the green one. I don't have labels in the target, but the distributions, the ratio of the distribution of the classes have changed. Okay? So that's the second thing that happens. And the third one is that these features, these things that I have, the measure features, they actually have uncertainty. You were asking during break. But these uncertainties, we can deal with them, maybe. But when we do transfer learning, the uncertainties may change so dramatically that your models don't apply. Okay, so those are the 3 scenarios that I discovered. The literature has totally different names, but this is the essence of it, right? Okay, so how do we transfer? Let's just, now it's very pedantic. We're not doing any Bayesian or any deep neural. Just let's say you didn't know anything about that. How do we transfer? Okay, so here's one way. I have my source, which is on the top, and I have the target, which is here. Okay, so first of all, I can do a generative model. So I model the top, my source, as 2 distributions, whatever the distributions are. In this case, I model them as a multi-Gaussians, and I do the same in the target. Now, I get rid of the data because I have generative models, and the only thing I have to do is to find the transformation between the 2. So what I do, now I have 2 Gaussians. Each Gaussian has a mean, and it has a covariance, mu and L. And the target has mu and L. So get rid of everything else. And the only thing I have to transfer now is the means and the covariances. Okay? So how do we transfer? One is some shift, which is nicely like that. Ooh. And this is described by some transformation T, translation. It can be a rotation, which is some rotation on the covariance matrix, which is described by matrix R, and some shifting, right? Which is described as some other rotation S. So if I model my things as Gaussians, I have these translations to discover. Okay, so now I'm going to do it in a Bayesian fashion. So everything is a random variable. So on the left, this is my target, Z is the class, and X is the data. And the X is described by some mean and some covariance. All these things are random variables except these hyperparameters here. I describe them in generative way, which is down here, the distributions. And once I have that, that's been done. That's the classic mixture of Gaussians. Yes, and I have the distribution of the classes, which are described as a categorical down here. And I can do the same in the target. So in the source, in the target, I model them both in a generative way, random variables. I can run that. But now, what I can do, I can put it together. And now what I have, on the left is the source, and on the right is the target. And what I have, the means and the covariance now are deterministic. They are not random variable, but the translation, rotation, and scaling is a random variable. So this becomes a generative model. We use MCMC to solve it. Okay? So this is the Bayesian approach to everything. And now we're going to move on to the next one. Okay. Now, in order to move to the next one, I need to describe a little more what the generative model is more than what I did. So imagine, and this goes a little beyond the talk, but Matthew put it up, so I put this slide very quickly. Imagine I want to make a generative model on a time series. So I want to generate time series like that. Okay? So how do we do that? What does it mean, generative model? We hear this term all the time. Let's just understand it. Okay? So I want to generate time series like so. So basically, I want to create a model that will create time series of that sort. Okay? So there's two ways of creating generative models. One is that you know the explicit distribution of your data, and one that you don't. There's explicit and implicit. The explicit is this variation Markov change, and the implicit, which is the new way of doing things, which is the GANs, which I'll talk a little bit later. Okay? So I don't need to know the intrinsic distribution. Okay. So I'm going to, again, go through this very simply. Let's say we want to generate data from a distribution. Let's say I want to generate data for this time series. So X will come from some distribution P of X. So that's what I want to do. So how do we do that? Let's say you want to generate data from a normal distribution. What do? np.random.norm? Okay, but how does it go under the hood? So let's say I want to do it from a normal. So anybody has an idea how do I do that? Yeah. You sample from uniform. Very good. So let's say I'm going to do for exponential. I'm going to sample from uniform. And then I'm going to find a transformation from the uniform. If I transform all my z's, which is the uniform, to x, such as the x is drawn from a distribution I want. In this particular case, x is equal to L, the log of z. If I take all the z's from uniform, and I take every value I draw, and I take the log of it, and I look at the distribution of it, it's exponential minus x. Okay? So that's the way you do it. You start with a uniform, usually, and then you do some transformation, and then you get the transformation, the distribution you want. For normal, you have to do 2, and you do some tricks there. But that's the basic idea. Okay? So I start with some z. Let's say it's uniform. I'm going to transform my z through some transformation g, such as x is equal to the 1 I want. Okay? And I have the true one. This is the estimated, and this is the true one. So now I have to compare what my samples I get with what I want. And how do I do that? We have some loss function, usually is some KL divergence. And in this particular case I was doing before, I was doing from uniform, and my transformation, it was LNZ. Okay? Now, this function from Z to LNZ, from Z to X actually, it's just a function transformation, right? It's a function estimation. And what do we know how to do function transformations? Which is the models that they do very well? Deep neural networks. They're the masters. It's a function approximation, master of function approximation. So I'm going to change this generator there with a deep neural network. That's all I'm going to do, and I have a generated model. Okay. So in order, though, to do that, I need to do one more thing to explain autoencoders, and everything will start coming into place. What is an autoencoder? It's a very, very simple idea. So I start, and I learned it from Nikos, by the way. First time I heard of them, 5 years ago, 6 years ago. You start with X, which, for example, is some image of the letter 2 from NMIS in this case. I bring it through some neural network here, and I encode it into some other dimensional space, usually smaller, H, and then I take the H and I decode it back. Now, if I go from 2 to a single number, most likely that number would not have enough information about 2. Right? In order to test if in the middle here the latent space has enough information, that means I can go from the reduce dimensionality back to my original one. That means there's enough information here to encapsulate this. Okay? So I start from here and I reduce it, and then I said, well, did I do a good job reducing it, or I reduced too much? Can I go back to 2? Okay? That's the idea of the encoder. So the loss function now will be, this is the graphical representation. The loss function will be from x through this encoding and decoding. That's what it does. So I take the input, I decode it, and then I go back and I compare what I got to what I have. If I can get it back, it means that decoding is very good. All right? So far, so good, right? Now, we're going to have variational encoders. Why did I talk about encoders? Because now, if I take just that part here, I start with z and I go to there. If the z, instead of having a number, if it was a distribution, I go from z to x. You remember my g of z, which gives me the distribution? That's what I have now. I have a generative model here. The only little thing I have to do, instead of going from the image to some number z, I'm going into a distribution here in the middle. And if I get rid of all these things here, I have z coming from some distribution, in this case normal, and then the transformation brings me back to the p of x I wanted all along. Okay? So this is variational encoder. Very simplistic. There's more to that, but I think that's the gist of it, right? So that means I can create a generative model this way. Okay? So next is to generate things without knowing the distribution, because here I insisted I know the distribution here. Okay? So that's the GANs. So I'll give you a very short introduction to GANs. So I start with my uniform, and then I go through some generative model. This is my transformation g of z to some p of x. Okay? And I have my true one here. So I need to compare these two. And you remember I said you do some comparison of the distributions like KL divergence. Well, I'm going to do something a little bit different now. So take it up. And instead of doing a loss function there, I'm going to put another discriminator neural network here, which compares the two of them. So this is how it works. I start with something here. I start with some uniform numbers there. And in this case, I'm making the time series that Matthew wanted. And this is the time series I wanted to generate, that type of a time series. So I start with some random numbers, and then I have a neural network which generates some time series randomly. Okay? And then it goes to the discriminator. The discriminator has to decide, is it a real one or is it a fake one? And if it says it's fake, it comes this way. And then it informs my generator saying, hey, you did a lousy job to create a time series. So I do that with my derivatives. I tell this. I adjust my weights on my neural network to do a better job. And now I did a better one. Okay? And then I go back and I said, still I understand this is a fake one. And I inform this, you did a bad job, bad computer. But not only that, I give you information how to move by looking at the derivative of my loss function. And now it did a better job. And now the discriminator thinks it's a real one. Okay, so now I'm telling the discriminator, hey, you got fooled. Improve yourself. And I tell him how to improve by looking at the derivative of the loss function. And the story goes on and on. So that's a way you generate without knowing the distribution by using the data. I think that's what Matthew was talking about. All right. So now I'm going to present a method we did. So when we did the Bayesian problem, one of the problems we have is that, you remember, I model everything as Gaussians. As a matter of fact, I model everything as a mixture of Gaussians. And the mixture of Gaussians is a good representation of any distribution, any PDF, but not always. So if you look at this, I have two classes, and I call them two bananas. Okay? Gaussians are more like oranges or apples. Okay? So if I try to represent that as a mixture of Gaussians, I'm putting a lot of oranges together, right? But banana does not go well with oranges, okay? So I need that was one of our problems, that our actual distribution of stuff, it looked like bananas, at least, maybe more spaghetti in some cases. So the mixture of Gaussians we used wasn't good enough. So we said, how can we transform these bananas into oranges? Encoders. So what we did, we took the bananas and we used an encoder to go into the encoding to the oranges, and then the decoding back to bananas. If my middle, the nice balls are good enough, it means I capture all the information and disentangle this banana situation. Okay, so that was the first idea. And then, of course, I modeled that as Gaussians now because I went to a space that Gaussians is a good approximation. Now, and one more idea. I have time. Well, you remember I said in my target space, sometimes I have labeled data. And I'm a believer when you have something, you should use it. So here's the idea of semi-supervised. So since I have some labeled data, I should use it. So the idea of semi-supervised comes in a very, again, very simplistic way of explaining it is the following. If you look at the blue and green, if I do a supervised, just ignore everything else, just use the blue and the green, I'm going to create this straight line classification model. Okay? It does very good. It separates the green and the blue. However, I have other data that don't have labels. I don't have colors. I don't have information. I don't know what they are. But if you look carefully, there is a gap in the density somewhere here. So in the semi-supervised regime, what you do, you take advantage of the labeled one, so you need to separate the green and the blue, but at the same time, you look at everything else you have, the unlabeled data, and you look gaps in your density in some ways. So now I came with a nice yellow thing. Okay? So let's put it all together, and this is the monster we made. Okay? So on the top, we have the target, which has nice labeled data. And we go through the encoder here, as I described, which brings them into this oranges situation in the middle, and my decoding at the other end. And then at the same time, you will take the target data, bring them through similar network. Actually, these layers are the same. And we encode it the same way, so they go into the oranges. So if these yellow go together and these blue go together, that means it's a successful. And how do I test that? I have here a classifier in the embedded space, in the reduced dimensionality space, in the orange space. And then I see how well I do by separating the yellow with the blue for both the target and the source and the target. Of course, the target doesn't have many, but I count how many mistakes I do. And at the same time, I'm making sure that this representation has enough information by looking at the reconstruction, meaning I decode it and see if I can get back the same thing. And at the same time, make sure that this, whatever I do here, it does look as a Gaussian. So my loss function has three components. Can I reconstruct? Do I capture all the information? Is it normal here? And does the classification work well? So if you put it all together and train a deep neural network, you get, okay, I don't think you need to say that. It's details. So we tried it on various data sets. Now, when we first tried the Bayesian thing, it wasn't working from a particular data set which is called HITS from Chile. Guillermo is one of the collaborators. It wasn't working very well, but Jorge had to graduate. Jorge Martinez is a graduate student. So he went and labeled them manually, unfortunately. Okay? So because the models were not working well with the first method we have. So, however, because he did manually label them, we have them for testing now. So we try to do transfer learning by going from macho to eros, which are very similar in nature, and then from macho to hits and all these combinations, right? So if we do just JM is for Jorge Martinez, without transfer learning, just train on his label data that he did. Has nothing to do with transfer learning. For these classes, I just keep 3 classes just to keep it simple. We get 70%, 99%, and 80% for 3 classes, eclipse invariant RLRs and quasars. If we use the model directly from Eros without transfer learning, we get crap. Okay, 1% accuracy is horrible. Okay, which is to be expected because they're very different. When we did the probabilistic transfer learning, we get okay for RLR, but the others were really bad. Thus, he had to go and do the labels. But when we did with this work, we get very good results. So if we have done this a little bit earlier, we save Jorge a few months of work, but that's the story right now. So in summary, 30 minutes exactly. We use the neural networks to encode a better latent space. We use neural networks to transformation, and it's great in nonlinear mapping. That's another thing I kind of forget to mention. The first approach we have, it's only linear mappings. You remember these matrices I have? They're all linear. In this case, it's not linear. We use generative model, and we took advantage of the semi-supervised learning because we use the data from even the little label data we have. And we show that the result extremely promising. And the future work now, what we're working on, talk to me later if you want, is actually we trying to do many, many data sets together, not just source target, but source, 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 target, target, target. And it goes around and it keeps learning and learning and it does everything at the same time. And thank you very much.
Thanks a lot, Pavlos, for this nice introduction of transfer learning, and Bayesian was used in there.
Yes.
Because I guess you cannot give a talk without using Bayesian.
Of course.
So questions, please. Nima?
Can you go back to the...
Wait a second for the screen, please.
Here, right?
Yeah. So if you didn't have any labels on the target set, what would it become? Like,
it still works because what you have, you see here we have a classifier, right? It's a simple classifier. Of course, some details with the reparameterization, but don't worry about that. You still get decent results, not as good. What we found out is that with only few examples in the target, it works much better. The problem is, if you don't have that, sometimes these balls here collapse into one, and you lose all the covariance things. And you need to do some tricks. But if you have some example in the target, it just converges much faster. But when I say few, I mean, in this case, 5, 10 is enough. 2 or 3, actually, in each class was enough to do it.
yeah, but then you would be left with only one loss, right? The reconstruction loss,
No,
I assume.
No, I do the classification error on those guys.
Ah, also they're on the embedded space.
Yeah, remember what I get this and I map them into embedded space, and at the same time I demand that the yellows will be in one and the blue will be in the other. Okay, one detail I didn't say, when you build this, you fix these guys. You fix your normal distributions. You fix them. 0, mean 0, 0, the other is mean 1, 1, and you fix the standard deviation. You fix them, and it's okay. You hope that the encoding will take care of it.
And one more question about the results. Very quick.
Yeah.
So I noticed you outperformed the original one.
Yeah.
So what is that? I mean, the first row is training.
The first one is only using, is a little bit different. The first one is using the label that Jorge did. So he did a training set, right?
Okay, on the target domain.
On the target.
Okay.
The last row there, we use very little, I think 3 or 4, I don't remember, anything between 3 and 5 of each class for the labels of Jorge, and the other ones are from Eros.
Okay. On the validation set or test set of the target domain?
Is from Jorge, yes.
Okay, thank you.
Hi, Pavlos. Nice talk. So have you tried training on the source data set and then doing some fine-tuning on the target data set?
Yes, you mean just
Just training on one data set and then
traditional classification, I mean traditional transfer learning, right?
Right, yeah.
Yes, early on in this game we did. It doesn't work very well because you're not taking advantage of these target distributions, right? So.
Thank you. I'm a little bit lost with
A little
what.
bit, that's good.
Well, a little bit. Well, I think I'm a little bit lost. So I'm probably very lost.
Yeah.
So when you go back to the complicated diagram,
You mean
when you go from this
one?
one,
Yeah.
when you go from your feature space, do the features have to be the same physical quantities?
No, this is a different dimension than this.
I understand. So
Yeah.
from your feature space, it could be periodicity versus luminosity.
Yeah, usually it's
But they have to be D1 and D2 have to be the same physical quantities. Is that right?
the same features, you mean? Yes.
Yes.
For this example, it has to be. However, you don't have to. We can change it. Because the way we build it, this network is common for both of them. So because of that, the feature dimensionality here and here have to be the same. However,
Dimension, but I mean, the physical,
the same. It has to be the same.
it has to be the same. It cannot be time
No,
versus
no.
meters or so.
However, I think, we haven't tried, you can add a layer here and a layer here that is for each one of them to bring them into the same dimension and go through.
But,
I haven't tried.
But it has to be also, I guess, the same underlying physical mechanism. So you cannot use periodicity
have
of
to, because
fireflies and learn from periodicity of fireflies to periodicity of Cepheids. Because I mean, you have the same measurements there.
You know, my gut feeling without trying is that it has to be, because otherwise the mapping between this space and this space are so different that I don't expect the same network to be able to do the mapping. So that's my guess.
I think if the same information content can be extracted from both of them. I think if the same information content can be extracted from both feature spaces, then the network is not going to have any problems in extracting them. But if that's
I'm not, honestly, I do not know. My gut feeling tells me if you have very different features, right? So let's say one you have colors, magnitude, blah, 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 and the other one you have position on the sky. I don't know. Something totally different. I haven't tried. My gut feeling tells me it's not going to work.
You could do, but I mean, the danger there is if you use things that have underlying,
Other side.
that have physically different mechanisms, like for example, fireflies have chemical reactions to power them, and while Cepheids don't. Isn't there the danger that you sort of like, fool yourself into believing that you have learned something, but you haven't?
Okay, but let's be, I don't know the answers very well. I don't know the answer, but let's be more precise. If you're talking about totally different objects, right? Then
Fireflies and Cepheids, for example.
yes, or I don't know, elephants and Cepheids, right?
Sounds great.
Okay. Again, I haven't tried, but my gut feeling is that it's not going to work, right? So what we're doing here is stars and stars and stars and stars. So the underlying process and the joint distribution in the feature space should be sort of, kind of similar, right? If you go from, it's like trying to learn English and then going to learn Chinese. I think the difference there, well, I don't know much Chinese to say, but I'm guessing that that's not the intention, to be honest with you. It's not to go from one domain to a very different domain. The intention and the application here is you go from one data set in astronomy to the other data set in astronomy. You may have some different populations. You may have some different population proportions that we tested with hits, but not from fireflies to Cepheids. But we should try. I don't know.
Let's give the others a chance
Yeah.
to ask. Ashish in the background.
So first to comment on the previous one and then the question. I think that if it quacks like a duck, flies like a duck, looks like a duck, you can declare it to be a duck, right? So that's why elephants and Cepheids, you should be fine, I think, if everything looks like. So question related to this, was there a physical or an actual overlap in the objects themselves between your two data sets?
On the sky?
Yeah.
No.
No, these were completely different sets of
I don't
objects.
think so, actually. Yeah. No, they're very different. I mean, on the sky they're not. Heats is, I don't think any of the heat fields falls into LMC. Yeah.
Could you go back, please, to the slide where you had generative adversarial networks?
Which one?
Go back. Yeah, this one, this one.
Uh-huh.
Yeah. So I was.
This is the best explanation of GANs ever, by the way. I claim.
And yet I have a question.
Yeah. It's okay.
So the secondary network, the discriminator neural network, how and when do you train it, or is it just a symbol for human brain?
No, it's here. Let's see. Stupid thing. It's here. So if I present with the fake one and the discriminator, which is a neural network, thinks it's a real one, I update the network there.
But to think it's a real one, or is it comes from the generator, it needs some kind of training set itself?
Yeah, I do training. Yeah. So you start, this actually works very well. As another talk. You start with with few examples, and you can generate, you can data augment, you can actually go beyond the physical perimeters, you can balance your training set, and I can honestly show you anytime you want things we generate with this network, and you won't be able to tell the difference between the real one and the other. It's amazing, and it can do irregular things too. But yeah, can I say one more thing? Don't try to train these things. Find someone else to do it. Preferably a graduate student, because they are. I'm on camera, right? Yeah. They're extremely difficult.
I think there was another question over there.
So it's kind of similar to previous questions, but you said, if I understand, no, but with stars. If I understand correctly, you said that it is possible to make your model kind of extrapolate to the data points which were not present in your training set. But problem here is that if you don't have labels for some kind of data, let's say that a concrete example that you have some objects up to magnitude 22, and you want to make predictions to some fainter magnitudes, right? So you would say that with your model is possible, but the problem I would see here is that it's not possible to actually, let's say that someone creates another model, and you cannot say which model is better, because you are always limited up to labels you have. Even if you do something outside of your labels, it's not possible to compare with anyone.
Okay, let me actually rephrase the question. As a good politician, I make it the way I want. So there's two things. One, when you generate things, yes, we can get away from the physical parameters a little bit. If you go far, things start breaking out. Now for the transfer learning exactly, you saying, well, if I go from a source to a target, and in the target I don't have to evaluate, how can you evaluate? And I think that's a valid statement. The evaluation, how well we do, it's only limited to what we have, right? Is that what you're saying?
Yes, and in this sense, yeah, like I understand that a big part of this model is to be able to work.
There's one trick we did, okay? I don't know if that will satisfy. Let's say you have all this data, right? And this is a parameter space. I take this and I hide it. So now I use this and trying to predict here, right? Yeah. And I have this hidden thing to validate, right? And then I validate and see how well I do outside the regime. That's the way we did it. And okay, so yeah. I don't know if that
I understand, but let's say considering the fact that right now we are only limited with spectroscopy up to some values,
sure,
it's not like this data still cannot be used. But
we did test to see how well it generalized within what we have. Now, if you tell me how does something looks at magnitude 36, color -5, okay. Yeah, okay. When we get data, we can test it.
I think there was a very, very quick one by
Dennis. Have 43 seconds.
So in this case, in cases of the GANs, do you always converge to a correct solution? Or
I said it's extremely difficult to train. Yeah. There's mode collapses. There is all kind of bad things that happen. But once it converges, it looks very good. But It's actually a very active research area now, how to get GANs to converge, but it's a painstaking.
Actually, my question was so about your last few slides, or your complex network, let's say. Would it also generalize for multi-classes, or is it always a binary selection?
No, this actually is, we do it for 10 classes. Yeah, okay. Absolutely. This is just a multi-class classification there.
Okay. Yeah. Thank you.
So let's thank Pavlos again.